Alright, so let's have a very brief vector refresher. In this class, we are going to move to thinking about much higher dimensional vectors. So if you've had Calc 3, this is the place where higher dimensions really kind of hit the fan. We're not going to do a lot of manipulations with higher dimensions because I trust that you own some kind of a device that can access the internet. If you don't own a device that can access the internet, boy, do you have a thing coming when you get on there. There's all sorts of stuff on that. I don't even know what to tell you. You're going to want to start with this, and don't go anywhere else. No. Don't follow links. Just live in the subreddit awe. It'll be better. All right. So, vectors are primarily two things. In physics, in trigonometry, in, well, ish in math. We'll see some examples that are a little bizarre later on. But in physics, at least, a vector is what?
Directions. Vectors.
Good. A vector is a little arrow like this. It has a magnitude and a direction. Are we good with that? Okay. The math world that we're going to start in is going to be two-dimensional vectors. Right? So I'm going to think this way. I'm going to make an R. I'm going to put a little 2 on it. That's going to be two-dimensional vectors. Is good with this? You guys are, in Calc 3, used to writing row vectors. I'm going to take that from you and write column vectors all semester because I live to confuse the shit out of you. It's just, oh, it's so much fun. Okay, so I'm going to make a vector this way. I'm going to start with the obvious example of the vector 1, 2. So, think to yourself, this is the vector that goes over 1, up 2, either. I'm not really basing that anywhere, but if we had to assume, it'd probably be based at 0, right? Okay. There are some operations we can do with vectors. Calc 3 students, what do you got?
Dot product.
Really? That's what you're going to start with?
Oh, okay. I'll start easy. Vector addition.
Good. So, we're going to start with addition, which I'm not going to circle because that means something else. We're going to start with addition.
Subtraction.
And the way you add two vectors, you go like this. You have a vector AB, you add to that a vector CD, and the way you get an answer here is what? What's the result of?
Plus C plus B.
Okay, so A plus C in the x coordinates and B plus D in the y. Good with this?
Yeah.
Okay, this amounts to the process of adding vectors by putting them tip to tail. So that would look like this. I have a couple vectors, which should be different lengths, because vectors generically are different lengths. And I think about this vector plus this vector is this third vector going from here to here. You guys with me? Okay. That's probably the last time we'll spend a lot of time thinking about adding them pictorially. I want you guys to just think this operation. Okay. The other operation that you have is what? What's the other basic operation?
Subtraction.
That's not an operation.
You have scalar multiplication.
Yup. Scalar multiplication is what I want.
Yay.
So, how do you scalar multiply?
Take scalar multiplication.
take a scalar and you multiply it. Okay, fair enough. What is a scalar?
Number.
A number.
No direction.
Okay, scalars are one-dimensional vectors, which is going to make a difference later. So a scalar, for our purposes, is going to be a number in R. So a scalar, a number in R. Guys good with that? This is a little bit up for grabs. We'll go into this more later, but for right now, it's just a number. So if you take a scalar, say k, and multiply by a vector ab, what do you get?
K, KB.
Okay. You get a new vector, the components of which are ka and kb. In terms of the picture, this does exactly what you would think.
Is it longer?
It makes it longer or shorter
Yeah.
by a factor of k. If k happens to be negative, it reverses the direction. Guys, good on board with this? Okay. Now, I need one more operation called the dot product.
I know what to do.
I don't know the cross product.
She doesn't know the cross
I
product.
do not
Should
know
we
the
start with the
cross
cross product?
No.
Okay, so the cross product is a perfectly valid thing to try to discuss at this point. It just doesn't work. Why? Why is the cross product not a valid topic for this particular board of math? Those of you who haven't had Calc 3, don't worry about this conversation. Just la 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 off to yourself for a
There's no
minute.
third thing.
Oh, yeah.
Yeah,
It's not.
the cross product is unique to 3 dimensions.
It's this guy.
It does not work in 2 dimensions, it does not work in 4 dimensions.
Isn't taking the determinant a cross product though? Kind of in a sense.
Backwards?
Okay.
So, let me give you an example. Every firefighter has a mustache, right?
Okay.
But not everyone with a mustache is a firefighter. So, the cross product is a determinant, but the determinant is not necessarily a cross product.
Dot products.
So,
Ready?
dot products.
AB cosine beta.
A dot, stop. A dot product is a way that you take 2 vectors and make a scalar out of it. Okay? That scalar has a bunch of meaning, which is why all the students who have had Calc 3 are like, oh my god, the dot product. Because, like, it's useful for stuff. It's really, really useful, and we're going to do a bunch of using it. Okay? But for right now, I just need a definition. So I'm going to take 2 vectors, and I hesitate. I'm gonna just do it. It'll be fun. Don't worry about it. Okay, so I want to dot product 2 vectors together. This is probably the last time I'm going to write dot product this way, because again, I live to confuse you, so we have different notation and stuff. So I'm dot producting these 2 vectors. Calc 3 students, how do you do that?
AC
times
Perfect. So you take the relative components that are in the same places, multiply those numbers together, and then add everything. So in this case, that's going to be A times C plus B times D. Are you with me on that? Okay. I'm going to put a little piece of geometry here, just because I can. And because it'll be handy later. So, this thing happens to be equal to the magnitude of the vector AB times the magnitude of the vector BC times the cosine of theta, which which is the angle between the two vectors. I'm writing this down today because it's so freaking handy that I just want you to know that this geometry exists. That said, I haven't defined this magnitude symbol yet, so you're maybe a little lost. We're at least lost only in that place.
Well, is it A, B, B, C?
Oh, it's A, B, C, D. What are we doing? Come on, Jim.
What?
It's the magnitude of the first vector times the magnitude of the second vector. Thank you. Okay. Good to hear, except maybe for the double bar symbol. Okay. I'm going to write the little double bar symbol right here because I want all this to fit on one board. So, the magnitude of a vector AB is perfect. The square root of a squared plus b squared. Okay. Anybody tell me where that probably came from?
Pythagorean.
Yeah, that's out of the Pythagorean theorem. That's the length of this thing. You guys with me on that? Okay. This is what I need you to know about vectors right now today. Pretty good with this. Okay.
Actually, I do have a question.
Hit me.
What is the, I understand theta is the angle, but is it the angle between the two vectors?
Yep.
Okay.
So that theta is going to be, here's one of your vectors, here's the other one, this is angle theta.
Okay, good.
That's going to give us some interesting consequences that I'm going to play with later. For right now, just throw it in there as a thought. It's going to give us something about the angle. We'll go into the specifics in a couple of days.
Great.
Any questions on the rest of this? Okay. These scale up. So if I did R4, a vector would be a little vertical box with 4 numbers in it. Scalar multiplication would work the same way. I would get a k on each of the letters. Addition would work the same way. You just add across. Dot product would work the same way. You multiply across and then add everything you get. Pretty good with those? Okay, that'll have us in vectors for a while. About 3/4 of the way through the semester, I think. And then I'll start telling you where I lied to you today.
I'm so excited.
You guys good with this?
Yeah.
Okay. Nothing here is fundamentally a lie. There just are other options for vectors later. They can be generalized a little bit. And so we're going to get some kind of other options other than like r to the whatever. Cool?